Okay, so this should be a fairly challenging one. We are diving into Chapter 4 of the Rust book Speedrun. Thanks for tuning in. Chapter 4 is what is ownership? We're going to do 4.1 and try to understand this concept. So this is the thing that lets it make memory safety guarantees without a garbage collector, borrowing slices, and how Rust lays data out in memory. Okay, what is ownership? Set of rules, how Rust manages memory. All programs have to manage memory. Garbage collection looks for memory no longer used. Sometimes the programmer has to do it. There's a third approach though, system of ownership. The compiler checks the rules. And it'll naturally make you good at safe and efficient code. Cool. So there's a learning curve, but it pays off. So we're going to focus on strings to learn this. Okay. The stack and the heap. Oh, this was touched on before. Excellent. So most programming languages, you don't care. It's been my experience. Yep. Stack and heap both provide memory, but they're structured differently. Stack stores as it gets them, removes them in the opposite order. Okay, classic. Last in, first out. Stack of plates. Pushing and popping. All data on the stack has to have a known fixed size. Unknown size data has to be on the heap. So heap is dynamic. Okay, the heap's less organized. You request some space, the allocator finds a spot that's big enough, marks it as in use, gives you a pointer to the address of that location. Okay. Allocating on the heap or allocating. I didn't know that. I didn't know that allocating was just short for allocating on the heap. Cool. Okay. Pushing to the stack is faster than allocating because the allocator never has to search for a place, so the OS doesn't have to do that work. Okay. You have to follow a pointer, so it's slower. You have to do math to get there. When you call a function, values passed into the function, and local variables are on the stack. When it's over, they pop off. Okay. Ownership addresses managing the heap, minimizing duplicate data, cleaning up unused data on the heap, tracking what parts of the code are on the heap. The main purpose of ownership is to manage heap data. Seems like a central point. Okay, good stuff. Ownership rules. Each value in Rust has an owner. There can be one at a time. When the owner goes out of scope, the value will be dropped. Okay, I am following along, so I'll put them in a main function. Okay, we have an ownership package. Let s equal hello. S is a string literal, hard-coded into the program, and it's valid until the end of the current scope. I wonder if brackets universally start and end scope. Is that always the case? The string type. So everything we've talked about was easy to push and pop off the stack because none of them were dynamic. String is an example of something that uses the heap. Okay, sounds like. String literals are immutable, but the string type manages data allocated on the heap, can store a dynamic amount of text. You can use from to get it from a literal. Okay, so we can turn this into a string like that. And it works. And we can declare it as mutable, and that does work. Now, if we call a string literal mutable, I think we had an error with that before, right? Let's make sure. No, that worked too. Does not need to be mutable. I'm confused, but I think maybe we just reassigned one string literal to another, and both of these literals are on the program, so they get hard-coded. I don't know. Maybe I'm just confusing myself. We can push str to the end of it. Okay, we can append memory and allocation. String literals are fast because they get hard-coded right in, but that's only because we know how big they are. Okay, so for a growable piece of text, we need some stuff on the heap. So we have to allocate it and we have to return it. So in C and C++, you have to call allocate exactly once or memalloc or whatever and call free exactly once for that call. I could see that causing problems. Memory is automatically returned when the variable owning it goes out of scope. Makes sense. Drop. So there is implicitly a drop call. Can we call that ourselves? Yes. Huh. And then what if we try to print it after we drop it? Haha, we get an error. Borrow of moved value. Resource acquisition is initialization. So there's a similar C++ pattern, but this is part of the Rust language. Okay, so we do it with primitives, if you can call them that, and it literally does just copy it and push it twice. This, though, does not copy the string object. A string has three parts: pointer, length, capacity. Makes sense. So that makes sense. If you need more capacity, maybe you allocate a lot on the heap and you make the string smaller, but you keep the memory. So capacity could be 5 and the length could be 3. So we copy the string data, but not the data that it points to. So you do get a copy of the pointer, you just don't get a copy of the heap data. So that could end up being expensive. Okay. Oh, double free error. So if you have this and S1 goes out of scope, it tries to drop that. S2 goes out of scope, it tries to free that memory again, that heap memory. Okay. Rust considers S1 no longer valid. Wow. Whoa, really? So S1's invalid now. Whoa. So it just changes the borrow? Is that what's happening? Crazy. Not what I expected at all. It's a move. S1 is moved into S2. Okay. Wow. Interesting. Rust will never automatically create deep copies of your data. So automatic copying is inexpensive. Deep stuff. Okay, variables and data interacting with clone. If you do want a deep copy, commonly you can use clone. So we can change this to s1.clone. Well, let me make 2 of these. Oops. There we go. So that's explicitly doing this. Okay. Stack only data copy. Oh, so you can call clone on this, but it does the exact same thing. No difference. Rust has an annotation called the copy trait for types that are stored on the stack, like integers. If a type implements it, variables do not move. Move meaning they go out of scope when you reassign them like this. Rather, they're trivially copied, making them still valid after assignment. Nice. If any of its parts has the drop trait, then you can't annotate it with copy. Wow, that's complex logic. Traits. Can't wait to learn about those. Type needs something special to happen, so it'll get a compiler error. Huh. Derivable traits. Beyond me for right now. Integers, booleans, floats, characters, and tuples. Or tuples. Okay. Copy trait. Good to know. Ownership and functions. Passing a variable to a function is similar to assigning to a variable. Passing a variable will move or copy, just as assignment does. Whoa, that's crazy. So you're literally pushing S into this function and it kind of just turns into a black hole and you lose your S reference. That would have confused me deeply if I encountered this without reading this book. Okay. But for things with the copy trait, it's fine to still use X. Huh, nice. Okay, I'll try it. Took ownership of 5 there, made a copy of 5. Okay, so we have the setup that they have here, and they're saying that if you try to say something about S5 after that call, that it's out of scope now. So if we do that, it should get an error. Compiler error. Wow, yeah. Now what if we do that for X? It should work. Yep, totally worked. Wow, okay. Return values in scope. Ooh, that makes sense. Returning values. Okay, so we don't necessarily always lose it to the black hole. What do we have here? Gives ownership, moves it to return type. Gives ownership, returns a string, so we return it. That's it. Is there anything special there? S2 comes into scope. S3 takes and gives back S2. Takes a string, gives back a string. Okay, that seems pretty straightforward. Assigning a value to another variable, moves it. When a variable contains data on the heap, it goes out of scope, clean up by drop, unless ownership has been moved to another variable. So doing it for every function is tedious. So what if we want it to use a value but not take ownership? So we don't have to pass it back, but we can have multiple Yeah, that makes sense because if we had more than one string here, and we wanted to return all of them, that would be a pain. We return multiple values with a tuple or tuple, but we can use references to use a value without transferring ownership. I guess that's next. But for now, we're stuck with tuples. Okay, wow. So I learned a lot from this one. I hope you did too. Thanks for watching. And see you for the next Rust book speed run here at PageKey Tech. See ya.